Greetings, everybody. This video will explain how to do the last um, online lab number 6, and I call it the Not So Simple Pendulum. And basically, what this lab is based on is that when we did remember, I think the last face-to-face lab we did was the simple pendulum and gravity, where we measured the period of a simple pendulum, and then using the formula for the period, we took that formula and solved it for G, and then I think we did the max-min method for the error. But when we did that lab, remember one of the conditions for the lab was that when you displaced the pendulum, you had to keep the angle small. And so what we did in the lab was, here's the formula we use for the period. This right here in the blue, t is equal to 2 pi times the square root of L over G, where L is the length of your pendulum and G is, of course, gravity. And then we rearranged that equation. We measured t, rearranged the equation, solved for G, then did our max-min method. But that formula, remember, one of the conditions for that lab was you had to keep theta, the displacement angle for the pendulum, you had to keep that angle small, i.e. 20 degrees or less. Well, in that range, for that range of angles, theta less than 20 degrees, well, you can use this formula. T is equal to 2 pi root L over G. That formula is based on this approximation for sine theta, that for small angles, the sine of theta is approximately equal to theta. Then that's called the small angle approximation. Using that small angle approximation, I didn't do the derivation for the lab, but that's how there's a very simple, you apply Newton's second law for rotation. You apply Newton's second law to the mass, a simple pendulum. Sum of the torques equals I alpha. And starting there, you can actually derive this equation for the period. We hadn't gotten there yet in class, so I just gave you this formula. But again, that formula is based on what's called the small angle approximation. Sine theta is approximately equal to theta, where theta is less than 20 degrees. Well, now what if notice here we're gonna in our simulation we're using values of theta from 80 down to 5 in increments of 5 degrees. Well, what if theta is not small? What if you're not using what's called the small angle approximation? Well, then what to do to derive the formula for the period? You first have to use the power series expansion for sine theta, and you have to keep the first two terms. So what you have to do is you have to use this formula for sine theta. Sine theta is approximately equal to theta minus theta cubed over 3 factorial. There are other terms, but to get a good approximation of the period, you just need to keep the first two terms in the power series for sine theta. So then, using this approximation for sine theta, you then get this formula for the period. T is approximately equal to 2 pi root L over G, parentheses, 1 plus theta squared over 12. We don't need to worry about the derivation, just take my word for it, that formula is correct. And so what it is if you're not limiting yourself to the small angle approximation, i.e. if you take values for theta that are greater than 20 degrees, as we have there, if you're not restricting yourselves to the small angle approximation, you first have to use the power series expansion for sine theta using the first two terms. Using this power series expansion, you can derive this formula for the period. T is approximately equal to 2 pi root L over G, parentheses, 1 plus theta squared over 12. And so what we're going to do is we're going to calculate the period not using, we're going to calculate the period, use it for even all of these angles. Actually, probably we don't need to. I guess that doesn't. In fact, let me pause this for a second. Okay, so what we're going to do is we're going to use running the simulation. We're going to get T-sim, the period from the simulation. We're going to get it for values of theta going from 80 then going down in increments of 5 down to 5 degrees. Then, and we're going to record the simulation period, the t from the simulation for each one. Then here in this blue column, the theoretical period, well, we're going to calculate it using the small angle approximation. So I'm only going to calculate the theoretical period. Remember, this small angle approximation, sine theta approximately equals theta, that's only good probably for value for theta at 20 degrees or less. So I'm not going to use, so I can't use this formula for these values of theta because it's not valid. So I'm only going to use this formula, t equals 2 pi root L over G. Notice I've entered it in right here. So I'm only going to use that formula for theta equal to 20, then 15, 10, and 5. Okay. Then what I'm going to do is, and then I'm going to just do the percent error just for the last four, because again, the blue is the small angle approximation. That's only valid if theta is less than or equal to 20 degrees. So I don't worry about it in this. Then what I'm going to do is I'm going to convert my theta to radians. Then I'm going to use now this formula for G using the power series expansion for sine, using the first two terms of the power series, and then you get this formula for the period. T is approximately equal to 2 pi root L over G, then parentheses 1 plus theta squared over 12. Well, this formula is good for any value of theta, you know. And so what we're going to do is I convert theta to radians. Then I'm going to calculate the actual period using that formula, and I'm going to calculate the actual period. You know, I'm going to, again, I have the simulation values. I'm going to calculate the actual values of t using this formula, and then do the percent error between the two. And we're going to do it, and remember, notice each of the equations for the period, whether we're using the small angle approximation or not, notice it's independent of the mass. So here I've just chosen a length of 0.7 meters. Then we're going to do the same thing, and we're going to do it for, cut the length approximately in half. And again, the blue column, that's the theoretical period based on the small angle approximation. The purple is the theoretical period where you're not restricting yourselves to the small angle approximation, using the power series expansion for sine theta, keeping the first two terms. If you do that, you know, you don't need to know the details, but you derive a formula for t. T is approximately equal to 2 pi root L over G, 1 plus theta squared over 12. And notice I've entered in the formula. See, for the small angle approximation, there's your theoretical period. For not restricting yourself to the small angle approximation, I've entered the formula in there. You're just going to have to copy the formulas down. Likewise, I already entered the formulas for the percent error. Just copy it down. Here, we're starting the percent error right there. All right, so what are you going to do? Well, let's go ahead. Here's the link to the simulation. Click on that and open it up. Start it. You're going to get three choices: intro, energy, and lab. We'll go to lab. Notice that over here on the right, the default value for gravity is 9.81. Just take that down to 9.80. The default length is 0.7. You can choose any length you want. You just want to use a length of, for the first sheet, use a length of 0.5 or greater. And then for sheet 2, just cut the length in half. Notice I did for sheet 1, I did a length. Notice my L is 0.70 meters. Then for sheet 2, I just cut the length in half. So you know. So let me go ahead and just set it equal to, okay, there. The mass doesn't matter, so I'm just going to randomly select the mass. No friction. Remember, those formulas are based on a frictionless simple pendulum. No, frictionless pendulum, not necessarily simple. Gravity, make sure it's 9.8. Then you want your period timer to show up, and the other velocity and acceleration and ruler and stopwatch, they're optional. If you want to have them, that's fine. If not, it doesn't matter. And now notice what the simulation allows you to do is you can set, see when I move the pendulum, you can set your theta, see? 24, 40 degrees, 51, 60. So what we're going to do is we're going to set theta starting at an angle of 80 degrees, see in the theta column, starting at 80, 75, 70, all the way down to 5. And again, the reason being that the purple column, we're not restricting ourselves to the small angle approximation. T is approximately equal to 2 pi root L over G, parentheses, 1 plus theta squared over 12. So we can use that formula to calculate the actual period, for any value of theta. Okay, so let me show you what we're going to do. So you open the simulation, and here's your pendulum. You want to make sure you have your period timer checked. And you want to make sure that gravity is 9.80 meters per second squared, not 9.81. That no friction none. The mass, set it on anything you want. And your length has to be, for sheet 1, has to be at least 0.5 meters. I've got mine set to 0.7. Now what I'm going to do is I'm going to take my pendulum, I'm going to displace it, I'm going to start at a displacement of 80 degrees. And see, then the pendulum's going to swing back and forth. And you can go normal or slow. It doesn't matter. Now notice I've got period timer checked. But notice you have to start the period timer. So I'm going to click here. And it'll trace out the one complete cycle. And then it'll give you the period. Okay. And there we go. And see, the period is the T sim, the period from the simulation, is 1.9101 seconds. And you can go ahead and pause it if you want. Doesn't matter. I'm going to take that number. I'm going to go to my spreadsheet right here. 1.9101. Okay, and notice the percent error over here automatically updated itself. And now now again do the same thing for 75 degrees. Okay, you got to stop it, of course, and then I'm going to set the angle to 75. Okay, of course you have to play, and then again it's a little bit tedious, but you have to go ahead and start the period timer. It'll go ahead and trace, and there we go, and then 1.8790. And watch what happens. 1.8790. Now watch what happens to, oh, well, never mind. Let me just, okay, hit check. Okay, then you're going to do the same for 70. Then what you can do is, so I would get all your simulation values first, and then go ahead, take the formula, just going left, right. So I would get all your simulation values first. Go ahead, do 70, then 65, then 60. I mean, very straightforward. I did 80, 75. I got to go do 70. Go ahead, start, period timer. We're done. 1.8508. I mean, you get the idea. It's not rocket science, so 1.8508, etc. So I would get all your simulation periods first. Then go ahead, take this formula, just copy it down. Everything should update automatically. Then go ahead to convert theta to radians. Go ahead, take this formula, copy it down. Okay. Then take this formula. Go ahead, copy it down. Percent error should automatically update themselves. And again, why we're doing this is we don't want to restrict ourselves to the small angle approximation. So to get an equation for the period, we need to expand sine theta in a power series. And for us, we just keep the first two terms. and then, and then go ahead and do the same thing, cut your length in half, and do the same thing. And again, I would get all your simulation values first. Okay, then take the formula for the theoretical period for the small angle, copy it down. Error should update automatically. Convert theta to radians, take that formula, copy it down. Formula for the actual period, not using the small angle approximation, take that formula, copy it down. Then to do the errors, take that formula, copy it down. And notice the difference. Notice here the theoretical period. Notice that it's 1.6793. Notice theta. If you use the small angle approximation, we'll end up with t is equal to 2 pi root L over g. So that number that number's not going to change at all. But notice you get 1.6793. Notice if you don't restrict yourselves to the small angle approximation, you'll probably get a slightly different value. But again, just get all the t sims, okay? Then go ahead, take this formula, copy it down, okay? The errors should automatically update themselves. Then take this formula. You need to convert theta to radians so you can use the second equation for t. You need to copy this formula down. Then this formula, so I've entered it in, just copy it down. Errors will update themselves automatically. Likewise for sheet 2. Get all your t-sims. Take this formula, copy it down. Convert to radians, copy it down. Take this formula, copy it down. And then the errors, I can do, copy it down. And you're done. So but basically, we're looking at, hey, what if we're not restricting ourselves to the small angle approximation? Well, you expand sine theta in a power series, and then you can derive a formula for the period. You don't need to worry about the derivation. Take my word for it. T is approximately equal to 2 pi root L over g, then 1 plus theta squared over 12 in parentheses. All right, so yeah. So there we go. Let me go ahead. And again, if you want to use 0.7 for your length and then 0.35, that's fine. Like I said, just for sheet 1, your length should be at least 0.5 meters. Then for sheet 2, just cut the length in half. So if you want to say you're using 0.9 meters, for trial 1. Again, you're starting at 80. Play. You have to start the period timer. And there we go. It automatically stops. So for a length of 0.9 meters for initial angle of 80 degrees, my period was 2.1659 seconds. Okay. Then do 75. You got to don't forget to start the period timer. There we go. I mean, you get the idea. It's pretty straightforward. And then for sheet 2, just cut the length in half. So I'm going to use a length of 0.45. Start at 80 degrees. Okay. Play. Start the period timer. And then there we go, period 1.5215. Yeah, and then the spreadsheet should update itself automatically. Alrighty, let me go ahead and save this video and get it posted.